Have you ever really stopped to think about how you can send a message to someone on the other side of the planet and it just gets there instantly? Well, today we're going to pull back the curtain on the amazing tech that makes it all happen. Let's get into it.
No, seriously, think about it for a second. It's not satellites, not for most of the stuff we do online anyway. So how does a video call, an email, or just a simple text message travel thousands and thousands of miles in the blink of an eye?
Well, the answer is actually kind of beautiful. It travels on a beam of light, zipped through a tiny strand of glass no thicker than one of your own hairs. Kind of poetic, right? Our entire digital world humming along on countless little beams of light. And in this explainer, we're going to show you exactly how that's even possible.
Okay, so first things first, we need to look at the actual physical network. Because here's a little secret. Our wireless world is in fact very, very wired.
The best way to picture it is like a global nervous system. There's this massive, hidden web of cables buried under our feet and stretched across the deepest parts of the ocean. And inside each one of those thick, rugged cables are thousands of those delicate little glass fibers, each one a highway for information. This is the real backbone of the internet.
So, how in the world do you trap a beam of light and force it to follow a path down a tiny glass thread? Well, the secret isn't some brand new sci-fi invention. It's actually a fundamental rule of physics.
It all kicks off with something called refraction, and I guarantee you've seen this a million times. You stick a straw in a glass of water, and right at the surface, it looks like it's bent, right? That's refraction. That's just what light does when it moves from air to water. It changes speed, so it changes direction. And that simple, everyday little trick is the first piece of our puzzle.
Now, let's take that idea and run with it. Imagine we're shining a laser through a block of glass. As the light leaves the glass, it bends a little. But what if we could tweak the properties of that glass, what's called its refractive index? Well, as we crank that up, the light bends more and more and more until it's almost skimming right along the surface. And that's when things get really interesting.
Because this is where the magic happens. If you push that angle just a little bit further, the light doesn't leave the glass at all. It bounces off the inside surface perfectly, like it just hit a mirror. This is it. This is the secret sauce. It's called total internal reflection. And just like that, we figured out how to trap light inside a piece of glass.
Okay, so knowing the science is one thing, but turning that cool principle into a technology that can literally wrap around the globe, that's a whole other challenge. That's where some brilliant engineering comes in.
So here's the problem you'd face. You've got your glass fiber, and the air around it creates that perfect boundary for total internal reflection. But that glass is incredibly thin and fragile. The moment you try to put a protective coating on it, you mess up that boundary and poof, the light escapes. The solution? It's just genius. They added a second layer of glass, called cladding, with a slightly different refractive index. This basically builds the mirror into the fiber itself, so now you can wrap it in anything you want for protection.
And this is what you end up with. You've got the inner core, made of silica glass, where the light actually travels. Surrounding that is the cladding, also silica, but with that lower refractive index to keep the light trapped. And on the outside, you have all the protective coatings that give it the strength it needs to survive at the bottom of the ocean.
Okay, so we've built our light tunnel. Now, how do we use it to actually send your hello text message?
Well, it's all about translation. First, your hello gets turned into binary code, a string of ones and zeros. Then, your phone turns that into electromagnetic waves. A 1 is a high-frequency wave, a 0 is a low one. At the other end, a transmitter sees that high-frequency wave and flashes a pulse of light into the fiber. It sees a low-frequency wave and does nothing. Light on, light off. 1, 0. Your message is now officially a series of light pulses, blinking its way to its destination.
So that seems to make sense, right? But sending that little pulse of light thousands of kilometers through an undersea cable, that's a whole different ballgame. How does it not just fizzle out?
Yeah, there's a name for that problem, attenuation. Even in super pure glass, the light signal gets weaker and weaker over long distances. So, the solution is to put amplifiers, or repeaters, every 100 kilometers or so along the cable to give the signal a boost. And you're probably asking, how do you plug those in at the bottom of the sea? The answer is pretty ironic. They run a thin copper wire the entire length of the cable, carrying old-fashioned electricity to power the new-fashioned light.
Looking at all this insane engineering, it really makes you wonder, why go through all the trouble? What was so wrong with the old copper wires we used for everything?
Well, to put it simply, it's not even a contest. Fiber is better in pretty much every single way. Speed? You're talking about light versus electrons. Light wins every time. Bandwidth? How much data you can push through. It's like going from a garden hose to a fire hose. Plus, since the light is trapped inside, it can't be affected by electrical interference, and it's way, way harder to spy on.
At the end of the day, it really all comes down to this number. That's the speed of light. You just can't beat the fundamental laws of physics, and that makes fiber the fastest possible way to get information from point A to point B on this planet, period.
And here's one last little surprising fact for you. Before fiber optics connected our world, they were first used to look inside the human body. That's right, the very same principle of guiding light down a flexible thread gave us the endoscope, changing medicine long before it ever changed telecommunications. Pretty cool, huh?
So when you step back and look at the big picture, it's kind of staggering. Our economy, our friendships, our whole digital lives, they all depend on this invisible network of glass threads. It's an incredibly powerful and robust system, but it's also built on something fundamentally fragile. It really makes you wonder, what does it mean that our entire civilization is built on these invisible threads of light? And where do we go from here?